next speaker is Stephen Chapra from Tufts University. He'll talk about the future of water quality modeling. I look forward to hearing about it.
This may be what the future is like. This is China in Lake Taihu. Okay, what I'm going to do here is, I've dropped a bunch of slides from this. This is a talk at the World Bank. So I've scaled it down. I'm going to talk about the 3 inevitabilities I believe of the future. And then we're going to talk about both global warming and mega urbanization. Global warming has many impacts on water quality. I'm going to focus on dissolved oxygen and temperature, and then harmful algal blooms. And then mega urbanization, I'm going to give 3 case studies that illustrate what I think water quality modeling is going to be used in the future in engineering applications. And then finally, I'm going to end on a 4th case study, which involves real-time distributed control in terms of a way to fight pollution, and then some conclusions. Okay, everything started in 19th century London as far as my field. And it was induced by the huge urbanization that took place because of the enclosures that were made in England. And what happened was that here's the population of London over time, and that abscissa, I can't even see it popping up until you came to the 19th century. And so at the end of this process, it was the world's largest city. So this urbanization that we're seeing today had big precursors during the Industrial Revolution. Just now, it's on a much bigger scale. At that time, there was one of the ways that they went and they controlled it, the sewage from London, was to have huge sewer construction. Sir Joseph Bazalgette was the primary engineer who worked on that. And what they did when they collected down at Beckton and Crossness, downstream of London at that time, and what they would do would be they would capture the sewage in huge tanks as the tide was coming in, and then they would discharge it as the tide went out. The idea was basically to share the pollution with France. Okay, but this effectively was really the start of sanitary engineering, now called environmental engineering. It's how engineers got involved in the natural world in terms of environment and ecology and things like that. Basically, where my field of water quality modeling came was with Streeter and Phelps in the United States, where basically engineers saw what happened in London, and so they built water treatment plants. And what they did at first was they just discharged their sewage from their collection systems into the river, the receiving water, as they did in London. But they rapidly, as London did, by the way, recognized they had to do wastewater treatment. And so what happened was the only sensible way to do wastewater treatment is to do some sort of a waste load allocation. In other words, if you want to figure out the waste loading, you have to go to some biologist or toxicologist to give you a concentration that is a critical concentration, a target in the water body. And if you can link those 2 things, the waste loading and the critical concentration, you can back calculate what waste loading you need to go and get the concentration correct. And that's where water quality modeling comes in. And basically all a model is it's an equation. It could be on a supercomputer, it doesn't matter, it's a function. And it says the concentration is a function of loading, and then the physics, chemistry, and biology of the water body. The subsequent evolution of modeling went through four major phases. There was a pre-computer era, which were closed-form solutions looking at oxygen. Then, as soon as computers came on, the physics is always the first place you get the advance. And so the hydrodynamics got refined, and so they moved to estuaries from rivers. Then in the 70s, that's where I became involved in the Great Lakes. But at that time, we were really focused on eutrophication. We expanded to lakes. We had biologists then become ascendant. And finally, in the toxics and acid rains, the 70s through the 90s, basically that's where our chemistry and our sediment water processes got upgraded. So at this point, the point of this is that we have the full suite of basically all the sciences and all the receiving water bodies have been modeled at one time or another. So there's still theoretical development going on. New pollutants come around. We have to look at new things. We're looking at things like nitrous oxide and different gases that we didn't look at in the past, but we have all the tools. In other words, this is a mature science at this point, a mature discipline. Now, when you do a water quality model, I like to do this with my students and just say, think of it as a simple equation where you've got concentration equals some constant coefficient times the loading coming into the water body. In other words, you're looking at it as a transfer function. And so basically, you've got stimulus system response where the physics, chemistry, and biology are embedded in that box in any kind of level of complexity. Now, I've given this slide for the past 40 years, and it changed a lot in the last 5 years, the reaction to this slide. Basically, the three ways that you can use that model is the forward calculation, concentration. You know what the loading is, I'll tell you what the concentration is in the water body. Then there's the inverse calculation, the one we just showed, where someone tells us a goal, concentration. We know how the environment works, and we back calculate the loading. There's this third way, though, which is the environmental modification design mode. And what that says is that you're kind of stuck with the loading. You have to basically kill all the people, move them out, to get any farther than you are at this point. So what happens at this point is you have to modify the environment. Now, for 38 years or something, I did that, and everybody said, why is he throwing the third one in? Because all the work up to the present was those first two things. I gave this in China, in Shanghai, several years ago, and basically all they wanted to talk about was the last one. Okay, and that's a major point of this talk. We have to shift the way we use models, and Philippe alluded to, right at the end, he said some stuff about releasing things from the reservoir. That's the way models are going to really be used in the future. Okay, the three inevitabilities are climate change. We have lost that war. You know, the horse is out of the barn. Mega urbanization, I see no reason why people are going to distribute globally. They're going to continue to concentrate in urban areas. And then I don't think there are going to be any miracles. In other words, some advance in treatment technology that's going to solve all our problems, the magic bullet that everybody thinks we can engineer our way out of it. So no order of magnitude increase in treatment technology. Okay, now, let's go to climate and focusing on water temperature and dissolved oxygen first. And basically, this plot, I think, is wonderful. It's the relationship of oxygen saturation versus temperature. And basically, you all know that as the temperature gets warmer, the water can hold less oxygen. That is exacerbated in saltwater system because the presence of dissolved solids go and reduce the saturation value. So what this says is that as the temperature gets warmer, you're going to have less buffer of oxygen. In other words, if you bring it down to zero or near zero, hypoxia, you're going to change the ecosystem disastrously. So a cold system has more resilience. It has more capacity for development than a warm system. If you're at high altitude, that exacerbates it too, right? Because the air is thinner at that point, the partial pressure is less, and so in those cases you have, so actually the worst case would be to go to Bolivia and have a saltwater lake. I mean, which, thank God, there aren't a lot of those. But this sets the stage for temperature being very, very important. Yeah, you're right, okay. No, but frankly, you see what I'm saying. If the temperature goes up, just in a very simplistic sense, places that have cold water fisheries are going to have warm water fisheries. That's like a take home from that. Basically now, warm water temperatures and harmful algal blooms. Basically, it's for harmful algal bloom HABs. In fresh water, they are cyanobacteria, blue-green algae. And there are many, many water quality impairments involved in it. It's a disaster as far as I can think of nothing good to say about blue-green algae, basically. Now, the principal components that make them win, right? You've got all these different species of phytoplankton, and they're competing. And the environment has a great influence on who wins the succession battle. And why do they win? Well, they love it warm. They are the oldest living organisms on the planet, at least for sure the oldest photosynthetic organisms on the planet. They've been through every ice age, every warming period. They're very, very simple, and so they're survivors. They're like cockroaches, where they say if there's a nuclear war, they're going to be cockroaches and cyanobacteria, the only thing left, okay? They also, their nutrient limitation, as Philippe mentioned, with nitrogen fixation, they have nuances there that give them an advantage. They can't be grazed, they can't be eaten, so you don't have a top-down pressure on them. And they can float. So they can basically shade out everything else and form unsightly scums. They're a disaster. Now, this is a very important plot. I apologize to the biologists in the audience, but with biologists, it's always hard to get them to be definitive about anything. He's laughing. You know exactly what I mean. And you figure, how do they justify their existence? But in any event, my friend Hans Perl basically came up with this plot, which is a meta-analysis of looking at data to come up with sort of general idea of the temperature tolerance. So that's growth rate versus temperature. And for things like diatoms and greens, which are the good algae, basically there'll come a threshold at which they cannot, it's sort of like fish, right? The same thing, salmonid, you go above a certain temperature, they can't survive. But the blue-greens, on the other hand, basically up to mid-30s, they pretty much are having a high old time. So if the water temperature gets warmer, you're going to get a succession over and above the nutrients. The nutrients are going to have an important part of it too, but you're going to just set them up for success. Now, this paper, we wrote in Environmental Science and Technology, where the EPA funded us to go and look at the continental United States, the contiguous United States, and basically do an economic analysis of the impact of climate change on harmful algal blooms. Funny thing happened in January 2017, our funding was stopped. I don't know what happened at that point, but I swear to God, anyway, I'm not going to vent. And basically what happened was, though, we had a model of the United States in terms of all the river basins, the major river basins. This work was done jointly with MIT, and they've been doing this for years, and we put the water quality part on top of their chassis of hydrology. And basically, what we found, read the paper if you want the gory details, but we did projections out to 2050 and to 2090, and what you see is that, large swatches of the United States are going to be, and that means dominated by blue-green algae, the dark green. But I would love to do this in Canada, or I would, as part of your thing. As soon as I saw this, I thought Canada, and then who did the one on England? There was a beautiful map of it. Was that Torsten? Yeah, it was. Okay. You could do that in these places, and you talk about global security, water security. This is the kind of thing that you can do, because the interesting part about this is you would suspect, if you asked anyone out in the street, they'd suspect the southern parts are going to be hit the worst. It wound up the biggest relative impact were the colder parts of the United States. And that's because of the fact that the way pollution works is it's a saturating sort of a relationship, where at the low quality levels, a small change in a loading has a big slope, so it gives you a bigger impact, and you come to a certain point, okay, so now I've got a boogie. Okay, mega urbanization, yeah, we got a lot of it. Important part about this is the slums nowadays are peripheral slums instead of the Dickensian interior part. I just want to quickly go through the Thames bubbler, the Sao Paulo. The thing with the Thames bubbler is that instead of doing waste treatment for combined sewer overflows, they deploy a barge with sensors in the river that detect when the oxygen goes down, and then they send these things out. It winds up being 100 to 1,000 times cheaper than retrofitting the sewers in London to go do this, okay? And China has its first one now in Shanghai. The Sao Paulo plastic bottles, this is what happens after it rains in Sao Paulo. Their thing to do there was to put up booms in the river, and then they get scavengers, who are mainly homeless people or very poor people, to queue up. They grab it, they bring it to the dump. So they've set up this little economy to basically go and to clean up this problem because it's impossible to stop any other way. Then finally, Haiti. Haiti is the cholera outbreak in 2010. Cholera was confirmed several months later. The first cases in 100 years, claimed over 8,000 people. More people died from cholera than from the earthquake. And what happened was, it's a widely held belief, which I widely hold, that basically it was the Nepalese soldiers that were responsible for it. Basically, cholera is endemic in Nepal, so they're non-symptomatic carriers. And so they came here and they defecated into these sewage ditches there. Let me show you where it is. This is the Arbanite River, which is lined with favelas down that river. That was the camp, and they went in. And what happened was the urbanization served as incubators for the disease. So someone who would drink at the headwater, get sick, you know, the cholera would be in them, out, goes down the river to the next place, so the concentration kept going up. This is what the thing looks like where the Blackwater disposal pit was. Now, this is hindsight, right? But what happened is there's an impoundment up there. And if they, after the first cholera thing, they had let water out of that dam, it would have just flushed it out into the Caribbean in about 12 hours, okay? And they didn't do that, and then you had 8,000 people die. So here's a case where hydrology, just as you with letting the water out of the dam, could be used, and possibly a model could help you in terms of deciding how to do things like that. Distributed real-time control, this is, I'm ending. Why am I getting so little time? I was watching the other guys. Come on. Imperial Valley. And this is a scheme. They have a very, very complex irrigation. It's one of the biggest ones in the world in Southern California. And my chemical engineering friends at the University of Colorado developed a distributed real-time control system there in which they had sensors all along. And they had control release points and things like that, coupled with the St. Fanon equation. In other words, so they had a very good hydrodynamic model to go and have waves going down the system. And they wound up, using control theory, minimize the amount that came out at the ends and into the desert, okay, which was waste, which was high salinity concentration. We could do exactly the same thing with oxygen, for example, and many other things, okay? Hey, conclusions. So the triad of global warming, mega urbanization, and the high marginal cost of waste reduction technology means that traditional wastewater treatment will be insufficient to solve future water quality problems, and environmental modifications based on real-time control and sensor technology, including remote sensing, will be commonly used to economically minimize the environmental impacts of many of these problems. Modelers have to stop doing the old thing, and regulatory agencies have to do that too. Give us the ability to do things at the least cost in the most effective way possible. Thanks.
We do have time for a few questions.
What?
Deprive people of that.
What? I like the wine.
Hi, thanks for the talk. First, cyanobacteria oxygenated the atmosphere, so that's pretty cool. But generally, they suck.
Yeah, right.
I agree. But yeah, I can think of one good thing to say.
I could argue with you about relative importance.
Sure, absolutely. The question I had was sort of related to involving ecological principles in water quality modeling. Specifically, like cyanobacteria, 4.2 billion years old, they divide once every couple of days. They evolve quickly, and we know that evolutionary scales and ecological scales they're not separate at the microbial world. Do you think there's a role for including evolutionary processes in providing forecasts for future water quality, particularly blooms?
Anything like that, I sort of shy away from it. Because again, you got to be a biologist. Because basically, no, whenever you tell them there's a problem, they go open loop. And basically, I'm sorry, and I love you, but the thing is that, no, they'll spin out 8,000 hypotheses, most of which can't be tested. But if you have, but the positive thing is absolutely. In other words, if you have not just that causes more uncertainty in the policy space. Mm-hmm. But if you have something like this, that's why we kept this parsimonious. this thing. I mean, it did the whole system, but it was like Torsten said, a simple approach to doing it. And we were going to do not that, but other things if our funding had continued that would have been plausible futures. Limited number of plausible futures, because again, I just, you know, politically, you can see that in the United States. I mean, if you can just make them be a little rational about this. No, I'm saying, you know, it's like the Middle Ages. And it's heartbreaking to see all that. We've both spent our whole careers doing this. And in my country, you know, so you have to be careful in terms, and I do it here. But I mean, but you have to be careful as how you put it out into the world. Okay,
thanks.
okay.
One more quick question.
Thank you for an interesting talk. Where do you think we should move forward in terms of improving our estimations of loading, particularly from agricultural areas? Loading, estimation of loading.
Loading.
Nutrient loading, for instance. And and how can we go about also reducing parameter non-identifiability? In terms of all the reactions we incorporate in nitrification, they tend to be first order reaction kinetics, but huge model structures, and then in the end we can have different parameters giving exactly the same result. So how do you think we should move forward into the future to try to solve this?
I'm a firm believer. First of all, I don't believe models. They're not God, but they're the best data synthesizing tools you can possibly have if you do them sensibly. So to me, they're a database. I mean, a model is basically a database that you can use to do extrapolation. And so what I would just suggest is that you model, if you're going to control, you model. And you have those couple things to guide your control. You don't just dictate control across the board. So,
Howard, did you want to just say something?
So one of the themes of this meeting, don't go away, Steve, is a 40-year time scale of some people's professional careers, mine in particular. But Steve was actually modeling the Great Lakes in the 1970s. So that hits our 40 years time scale. So could you just say a little bit about how you think modeling capability has evolved for the Great Lakes systems over that period and where it should be going over the next few decades?
I'm going to be negative about this. I'm going to be negative, and it's something that's actually you could remedy here, this group, this university. But what typically happened was they did the work for the first water quality in the 70s, and then they decommissioned models. They went and stopped measuring Lake Erie in the 90s because they'd solved the problem. And then the zebra mussels came in, and boy, wouldn't it have been good if we were watching when they were sneaking in. And so what I've always, I proposed this 40 years ago, that every important water body in the world should have a living model that has someone who's the hero that maintains that model or a group. And I thought Environment Canada would be it. I even proposed giving them Michigan so that Lake Michigan would be in Canada, because they don't mark, you know, because, anybody here from EPA here? Well, I'm on their shit list anyway. So Canada does it right. So to me, with Diefenbaker, the way you're looking at this from a watershed perspective, those sorts of things, when you leave and when Carl retires, or the whole thing gets taken apart, and then it gets put on a shelf as a report and there's been some papers from it, I think that's criminal. I mean, to me, so that's my biggest, and it was partially my fault because I left. No, really, because I was the guy who was doing the systems model at that point, and I had a minion that they hired to take my place, and then I told him, you should be just, because then we got land use, we had GIS, and it never got put into the framework. Now they're sort of doing it, and again, what was Elaine? Had some things that were really lifting my spirit, but somebody should go and do that. And then have the ability to use the models to guide how you steward the system. That would be my ideal world, and I'm going to die before that happens. Although, if it's going to happen, you know, it's going to happen in China. No, because they're right on top of it. No, but he got me there the first time. Second time, it was Tongji University in Shanghai that got me there. Every time since, it's been the government now who poo-pooed all this stuff, no pun intended, in the past, okay? Now that they're, and boy, what if they decide to do Taihu and do the whole basin, they're gonna do it. So that's my answer.